So quick talk on likelihood ratios and probabilistic reasoning, just what you guys wanted to hear about when you woke up this morning. So the problem is that we start with a person, we have some disease on our differential that we're concerned this person might have. So we run a test, we get the results of that test, and then we're left with this big question mark. Does this person have the disease or not? If tests were perfect, obviously it would be easy. The test would be positive and they had the disease, or the test would be negative and they don't have the disease. Unfortunately, as we all know, it doesn't work like that. So when we run a test looking for a disease, what is it based on those results? What do we want to know? Somebody tell me, what do we want to know based on the results of that test? Anybody? I know this is Zoom, but somebody shout it out.
So Dan Greenstein says,
is everybody muted for some reason?
Let's see.
Does it increase the likelihood of, or decrease the likelihood?
Okay, does it increase the likelihood or decrease the likelihood? Here, let me go back to this. Okay, so it either increases or decreases, but what do we really want to know? We want to know, based on the results of our test, what is the probability now that our patient has the disease? So you're right. So the test is either going to increase or decrease the likelihood based on the results. So the question now is, well, now what's our probability that our patient has the disease? So we have different test characteristics to try and help us answer these questions, but they don't necessarily tell us what we want to know. So we often think of sensitivity and specificity as being our go-tos, but sensitivity is the probability that somebody with the disease will have a positive test. Well, that doesn't help me clinically, does it? Because I don't know if the patient has the disease or not. And I don't care what the probability of the test coming back positive or negative is necessarily, at least clinically. I have the results of the test. I know if it's positive or negative. Now I want to know if the person has the disease or not, or what probability they are of having the disease or not. Specificity has the same problem. It's the probability that someone without the disease will have a negative test. Same problem. I don't know if they have the disease, and I already know what the results of the test are because I got the results back. So that leaves us with predictive values, which on the face of it are going to look perfect. Because what does a negative predictive value tell us? It's the probability that somebody with a negative test does not have the disease. That sounds like exactly what we want, right? And a lot of these studies report negative predictive values for that very reason, because it sounds on the face of it like that's the answer we want to have. And I'm going to show you guys why there's a flaw there. Positive predictive value, by the same token, is the probability that somebody with a positive test has the disease. It seems like it answers our question, but again, there's a problem there. So the problem is prevalence. Positive and negative predictive values vary as the prevalence of the disease varies. So we're talking about the same test in both of these figures here. This is the same test, but in two different patient populations. The sensitivity and specificity of the test are 95%. That doesn't change with the prevalence of disease, at least in theory it doesn't. And you can see in these two squares here that the sensitivity and specificity are the same. But what about the positive and negative predictive values? Well, here on the right, we have a very highly prevalent population. So the disease is present in 95% of the patients in this population. As a result, if you do the test on a ton of people most of whom have the disease, and it comes back positive, well, it probably means they have the disease. So again, a positive predictive value greater than 99%. But again, very few patients in this group had the disease. So the negative predictive value was awful, only 50%. On the other hand, on the left here, where our disease prevalence is very, very low, only 5% of patients had the disease, our positive predictive value now is only 50%, whereas the negative predictive value is great. It's greater than 99%. As some people will say, if you do a test on a bunch of people who don't have the disease, it's probably going to come up negative in most of them, right? So we now are stuck with sensitivity, specificity, which we said don't answer our question. Positive and negative predictive value, which seem like they do, but they don't take into account the prevalence of the disease in the population. So we need something else. Our ideal test is something that's going to take into account the pre-test probability of the disease, or the prevalence in our group of patients that we're specifically looking at. Then once we have the test back, we know or find out what our post-test probability of disease is, the probability of the disease now that we know the results. And this is where likelihood ratios come in. Does anybody know who this is? I'll be shocked if anybody does. It is not Greg Polides. Looks a little like him. So this is Thomas Bayes, who is a famous statistician who came up with Bayes' theorem or unconditional probability. You don't have to worry too much about what this is, but basically what this says is that the probability of A being true, given that B is already true, is equal to the probability of B being true if A is true times the probability of A divided by the probability of B. Now, that's just a bunch of nonsense. But if we throw in there diseases and tests, it starts to make a little more sense. So now we have the probability of the disease being present if the test is positive on the left, our post-test probability. And on the right there, we have the prevalence of the disease, our pre-test probability. And what this allows us to do is to use this formula to create likelihood ratios that are going to help tell us the probability of disease based on pretest probability after the test comes back. So likelihood ratios. These are the formulas for them. You don't have to memorize them, but they're good to know. Positive likelihood ratio is the probability of having a positive test if you have the disease divided by the probability of having a negative test if you have the disease. Negative likelihood ratio, on the other hand, the probability of having a negative test if you have the disease divided by the probability of having a negative test if you don't have the disease. But more importantly, let's talk about how they're used in application, because that's what we really care about. So you start with a person, you run a test. Now that you have the test back, you can figure out the post-test probability by applying these likelihood ratios to the pre-test probability. So the test comes back positive, your pre-test probability, and you can use that to figure out your post-test probability. And let's show you how you do that. So there are a couple of ways. Oh, wait, hold on. Same thing with negative tests. This is all that is. We'll run through that. First is this phagon nomogram. So Arthur, when you were talking about likelihood ratios, you said something to the effect of that if your positive likelihood ratio is 25, that means you're 25 times more likely to have the disease. That isn't really true. Your odds of having the disease are actually 25 times higher, which is hard to think through, but it's not like you take the pre-test probability of say 2%, multiply it by 25, and now your post-test probability is 50%. It'd be nice if it were that easy, but it's not. This phagon nomogram, though, allows you to start with the pre-test probability on the left, draw a line through your likelihood ratio, and you'll end up at your post-test probability. In this case, if your pre-test probability is 10%, you have a positive likelihood ratio of 10, your post-test probability is a little higher than 50%. So now your test came back positive. I now know that you're a little more than 50%, have a little more than 50% chance of having whatever disease it is we're looking at. So you can use the phagon nomogram for negative likelihood ratios as well. If you start with a 35% probability, sorry, a 25% probability of disease is your pretest probability. Negative likelihood ratio is 0.2. Now your post-test probability is 5%. So we've reduced your risk by having a negative test. You can use these phagon nomograms, or you can use online calculators, which are much easier to use and are going to give you a more accurate result. There are a bunch of them online. These are just a few. So let's apply this real quick. Or sorry, before we get to that. So what's a good likelihood ratio? There's no absolute number. We tend to think of positive likelihood ratios greater than 10 as giving us a large change in the probability of disease when the test is positive, and a negative likelihood ratio of less than 0.1 is giving us a good large decrease in the probability of disease. For positive likelihood ratio, a 2 to 10 is kind of moderate. 1 to 2 is pretty small change. For negative likelihood ratio, 0.1 to 0.5 is moderate. Anything between 0.5 and 1 is a small change. And again, a likelihood ratio of 1 means there's no change in probability. So how do you figure out what someone's pretest probability is? Either by knowing the known prevalence of disease in a patient population, so probably more applicable to oncologists and cancer, using clinical gestalt, or by using clinical decision rules, and we'll talk about how we do that. So let's talk about, real quick, we're going to talk about our patient in our vignette. Pull up our heart score calculator again here. So I think I wrote in the vignette that the patient had a heart score of 3, and someone pointed out it was actually probably 4 because they had moderately suspicious of disease. They were between 45 and 64. They had greater than 3 risk factors. So heart score of 4, which puts them at a 12 to 16.6% risk. So going back to the PGY II study, pull up the numbers here. If you had an initial troponin less than 6, your negative likelihood ratio for the disease was 0.17. So if we apply that to this patient, we're going to enter a risk of, let's say, 15%, which is between that, what was it, 11 to 16, or 12 to 16.6%. And now a negative likelihood ratio of 0.17, which I'll put right there, and we calculate the risk. So now if the test is negative, the post-test probability is 2.9%. Now they've mentioned a negative predictive value of over 98%, so your risk was less than 2%. But again, that's all comers. If we look at a patient who's at more of a moderate risk like our patient, we're still at about a 3% risk of disease. If on the other hand, we looked at a patient who was coming in with that crushing substernal chest pain while they were shoveling snow, which is just a high risk thing for someone who's over 65, even with a normal EKG and a bunch of risk factors, and some non-specific changes on their EKG. Now their risk is more, their pretest risk is 50 to 65%. So this is a high risk patient. And if we enter that pretest probability of 50%, even with a negative diagnostic test, even with a negative initial troponin, our risk is still 14.5%. So even though that negative predictive value was greater than 98%, if we're looking at moderate to high risk patients, our risk is higher than that 2% that they are touting. So you have to be careful. You can't apply these numbers, these negative predictive values, to all patients. If you do that, you're going to miss the disease in a lot of the sicker patients and the ones who are higher risk. So that's why likelihood ratios help us a lot more than negative predictive values, because they take into account the pretest probability or prevalence of disease in particular subgroups of patients. So one last thing, and then we'll be done with this, is you don't have to use a strict cutoff when you're using likelihood ratios. You can actually use something called an interval likelihood ratio. So here, looking at white counts for patients with appendicitis, rather than just use a cutoff of, say, 10 or whatever it is. I think it's 10 in our institution. If you have a white count less than 8, you can see that your likelihood ratio, negative likelihood ratio, is 0.2. If you have a white count of 8 to 15, you now have a slightly positive likelihood ratio of 1.3, and a white count greater than 15, your likelihood ratio is up to 7. So you can break these down to whatever intervals you want. Keep in mind, the more intervals you have, the smaller number of patients in each group within that interval, your 95% confidence interval for your likelihood ratio is going to be wider and wider.